Good morning, guys. Today we're going to look at geometric transformations with matrices. We've already looked at adding matrices, multiplying matrices by a scalar, and multiplying matrices together. Well, we can use all of those processes and operations to be able to take geometric figures and move them around in space. We can translate them, which is shifting them or moving them left and right, up or down. We can dilate them, scale them, make them bigger or smaller, stretch or shrink them, and we can make them flip across an axis or even rotate around, all using either matrix addition, scalar multiplication, or matrix multiplication. Before we can do that, though, we have to get our geometric figure into a matrix. So we start with our coordinate matrix, and that's just taking the x coordinates and making them one row, the y coordinates making them the other row. It doesn't matter which row you do what, but just typically we do x's then y's, so I just will have my x's as my first row, y's as my second row. So you'll see every matrix that we work off of will be a 2 by something matrix, and the something is however many points or vertices we actually happen to be working with. First one we're going to look at is the translations. So that's shifting this thing left and right or up and down. So to translate, we're going to take a coordinate matrix and add it to a translation matrix. And that just goes back to when we do our geometric or our transformations of functions. If I want to move a graph vertically, I want to add that amount onto all the y coordinates. If I want to move it horizontally, I'm going to add it onto the x coordinates. Same idea with translations because, or with matrices, because that's all we're working with is the x and y coordinates. So a translation matrix is going to be set up like this, where the top row is going to be the h's, bottom row is going to be the k's. That's because h is the amount and distance that we're transforming or translating it horizontally. How far and in what direction are we moving it horizontally? Since x's are on the top, I put my h, my horizontal translations on the top. K is going to be the vertical shift. So since y was in the second row, my k's will be in the second row. Now remember, because when we add matrices, that's what translating is, when we add matrices, we just combine corresponding. So this first x coordinate is going to get increased. I'm going to get moved over this far. The second one will get moved over the same amount. The third one will get moved over the same amount, and so on. The y's will get moved up the same amount as we go through. So let's just look at a quick example of translating. Let's take this figure right here. So I will start by writing out my coordinate matrix. So my ordered pairs are going to be the point -1, +4. So -1, +4. The orders I do these rows in don't make any difference, or do these columns in don't make any difference. 3 by 1, so 3, 1. And then we've got -2, -1. And let's say that we want to move this figure, I don't know, right 2, and we'll move it down 3. Right 2 and down 3. So right is a horizontal move. So that means since these are my x's, these are my y's, this has to be my horizontal, this has to be my vertical. So right 2 is +2. We want to increase all our x's by a value of 2. So we're going to put 2 right here. We got 3x values, so I need to have 3 values adding 2 on there. Vertically, down 3 is 3 units down, is -3. And if we do the arithmetic of adding, because that's all a shift or translation is, if I add, I'll get this new matrix, -1 + 2, 3 + 2, -2 plus 2, 4 plus -3, -3, 1 plus -3, -1 plus -3. Do the arithmetic on it. 1, 5, 0, 1, -2, -4. If we graph that new figure, I'm at the point 1, 1. I'm at the point 5, -2. And I'm at the point 0, 4. So you can see we get the same figure, we just moved it right 2 units and down 3 units. Every point, over 2, down 3, over 2, down 3, over 2, down 3. So that's shifting or translating. As long as your X's then Y's, you do horizontal shift over vertical shift. Next, let's look at dilating a figure. That's either compressing it or stretching it out. It's going to keep the same shape. They're going to be proportional figures, but there's just going to be one larger and one smaller. The way we do that is just by using a scalar of dilation. You may see it called. And we know that scalars we just distribute to every figure. Now this process only works when the center is at the origin. You can see mine's a little bit off, but we'll get a general picture there. There's actually a little bit more involved with the formula to scale it down when the center of dilation is not at the origin. But we'll look at that in class. So kind of be thinking about how you think we can get from a figure out here to shrink down while still keeping the center in the same place and just compress where it's at or expand where it's at. But right now we're going to look at figures, and your book work is also going to be centered around figures that are, or focused on figures that are centered at the origin. So it's pretty straightforward. You're just going to distribute your scalar like we did with our scalar multiplication. So we get 1/2 times 1 is 1/2. 1/2 times 2 is 1. 1/2 times -3 is -3/2. 1/2 of 4 is 2. 1/2 of -2 is -1. And 1/2 of 1 is going to be 1. And let's plot it and see if we get a figure half the size of this one. 1/2, 2. So over 1/2 up 2. Over 1, down 1. Back 1.5, up 1. So we get this figure, which is, again, when you're centered at the origin, everything's getting pulled in. But you can see it's half the size that the original value was. It is just kind of rotated a little bit only because my scale is off and we're not centered directly at the origin. This would also be centered at the origin. So when you multiply by a scalar, it compresses everything back towards the origin by that much, or expands by that much. Because we're multiplying every value, x's and y's. So that's the process for dilating when you are centered at the origin. Again, we'll look at how to do it when it's out in space. So if I get kind of thinking about that. Next, we're going to look at how to reflect across one axis. So say we want to reflect this across the y-axis. So we're going to reflect it horizontally. What's happening with the points when we reflect it? They're at the same height, so our y values, we don't want them to change. And the x values are the same distance from the y-axis. We just need them to become opposite. So I need this +2 to become a -2. This +3 to become a -3. The +4 to become a -4. So what can I multiply each of these by? What could my reflection matrix be? Because we just talked about before that if I'm going to change the numbers scale-wise, we multiply. When we'll change their signs, we also want to multiply. So what could my reflection matrix look like? Well, we know that, as we talked about matrix multiplication, if I want to leave just the numbers alone, I multiply them by the identity matrix. So this is a 1, 0, 0, 1. It's a 2 by 2 identity matrix because I need my 2 by 2 to go with my 2 rows by 3 columns, inside numbers match, columns from the first, rows from the second. So that tells me I need a 2 by 2 matrix. That's going to leave it the same. Now, what can I do to this to make these opposite? Typically, we make opposite by multiplying by -1. Well, where do I put that -1? I need to put it somewhere that only affects these x coordinates, because I'm talking about a horizontal flip. So if we look at it, and let's just try it out. If I multiply by the first row, by the first column, 1 times 2 is 2, 0 times 4 is 0, 2 plus 0 gives me the 2. Well, I don't need this to be 2, I need it to be -2. So I don't want to multiply by 1, rather I want to multiply by -1. Well, let's see, do I need to change this 1 to anything? So if we look at it, -2 plus 0 will give me a -2, which is what we want. Well, let's look at my y coordinates, how they're impacted. They're working off row 2. Because remember, when we have our product matrix here, row 2 is going to be my columns, or sorry, it's going to be my y's. So it's going to work off of my row 2 for matrix 1. So if we look, 0 times 2 is 0, 1 times 4 is 4, so 0 plus 4 will give me a 4. So a 1 sitting right here will leave all those y values the same. A -1 sitting here will have all the x values go opposite. So this is our horizontal reflection matrix. Well, let's do the math, see what it looks like. So again, rows by columns, we'll have 2 rows, 3 columns, 2 rows from the first matrix, 3 columns from the second, -2 plus 0, -3 plus 0, -4 plus 0, slide over here, 0 plus 4, 0 plus 1, and 0 plus 2. So multiply first times first, second times second, and add those all together. Do the arithmetic, -2, -3, -4, 4, 1, 2. So you see by putting that -1 on my x row, it made all of my x's go opposite. The +1 on my y row made all my y's stay the same. Well, let's see if that actually gives us our reflection, that horizontal reflection we were looking for. So I'm going -2 up 4. I'm going left 3 up 1. I'm going left 4. That up. Left 4 up 2. So you can see we get the same figure flipped across the x-axis. Well, what if we wanted to do it vertically? So I wanted to flip this thing down. So if I want to flip it across the x-axis instead of across the y-axis, what needs to change in our reflection matrix so that we can get a vertical reflection? X's are going to stay the same because we're going to stay on the right side of the y-axis. The y's are going to go opposite. So our negative needs to be on the y row. So as we check through, +2 and 0, +3 and 0, +4 and 0. So all those go positive. 0, -4. 0, -1. 0, -2. So we can see that we have 2, -4. Over 2, down 4. 3, -1. And 4, -2. Same figure flipped vertically now. Okay, so we can flip it horizontally by putting the negative on the X row of the identity matrix, or horizontally on the negative on the X row of the matrix, identity matrix, vertically if we put the negative on the Y row of the identity matrix. Now that's all assuming you have X's as your first row, Y's as your second row. If you flipped that, then the relationship would flip here also. So we just looked at reflection matrices, flipping it across the X, flipping it across the Y. So if we put the negative on the X row of the identity matrix, we go horizontal. Y row, we go vertical. So what do you think happens if we put a negative on both the X and the Y? Should flip us horizontally and then vertically. So is that a reflection? Well, let's look at it. So if I go in, -1 on top, we know that's going to just be negative on all the bottom because we get, or negative for all the tops because the zeros will be for the bottom. So we would get -2, -3, -4. We just looked at that. All right, same thing here. 0 wipes out that top row, and we're just left with negative for the bottom. -4, -1, -2. So if we go through and do our matrix multiplication, rows by columns, and so on, we should get this matrix. So when I plot this, I get -2, -4. I get -3, -1. I get -4, -2. So I don't get, ooh, that was awful, a reflection, because if it was a reflection, this point would be over here. We'd get the same shape, just reflected. So if we were trying to reflect across Georgia, what we actually get is a rotation. It's been turned all the way around, and it has rotated 180 degrees. So this actually gives me a 180 degree rotation. Now there are two other rotation matrices that we're going to focus on. That's 0, -1, and 1, 0. And then there is 0, 1, and -1, 0. Now, if we look at these for just a minute, what changed in general from here to here is we took our identity matrix and we swapped the rows. So what do you think swapping the rows here should do to our product matrix? If you go through and do the multiplication, it's going to swap. So now this is saying I want none of row 1 and I want all of row 2. It's just going to be opposite. So by switching the rows and columns, sorry, the rows from our identity matrix, we've actually switched the rows back here. So that's what builds our rotation. So if I go in and do my multiplication, 0 and -4 is -4, 0 and -1 is -1, 0 and -2 is -2, and for the next one, 2 and 0 is 2, 3 and 0 is 0, sorry, it's 3, and then 4 and 0 is 4. So you can see that these rows have swapped places because these rows swap places. So that's another manipulation that you can do. Now let's look at what that does graphically. Left 4, up 2. Left 1, up 3. Left 2, up 4. So what changed from here to here is we have rotated around -90 degrees, or we have gone, sorry, that would be positive 90 degrees. We'll talk about that when we get into trig. But we have gone counterclockwise 90 degrees. So this is our counterclockwise 90 degrees rotation matrix. Well, let's look at the last one. We're going to again flip these two rows. I'll flip these two rows. Do this in red. Let's stick in blue. I'll graph it in red, but we'll do the work in blue so we can see it. So we know that it's going to be 4, -1, 2, 2, 3, 4. Swapping the rows of the identity swaps the rows of the original. and the negative is on the second row, so that would put the negative on the second row values. Go through and do the math if you need to. 0 and 4 is 4, 0 and 1 is 1, 0 and 2 is 2, negative 2 and 0 is negative 2, negative 3 and 0 is negative 3, negative 4 and 0 is negative 4. When we graph this, over 4 down 2, over 1 down 3, over 2 down 4. Still says same figure. All we've done is rotated it 90 degrees. Okay, so we've gone 90 degrees clockwise. Or you could look at it as 90 degrees counterclockwise, 180 counterclockwise, that'd be 270 degrees clockwise. And then the 1, 1 would put us back where we started. So we could technically look at that as a 360 degree rotation. So these are our rotation matrices for going 90 degrees at a time around the origin. Again, if you're going to want to rotate a figure around itself, you're going to have to manipulate this process. And we'll talk a little bit about that in class tomorrow. So those are all the types of transformations that we use matrices to perform on geometric figures. Remember, they all do work around the origin with the exception of the translations, the shifts. But we have ways to adjust that, and we will discuss those techniques in class. So kind of be thinking about how you think we can rotate something around itself in space and not the origin, or how we can rotate or dilate something in space. If you're wondering, these formulas here, these rotation matrices, they come from some trigonometry we obviously have not covered yet. We'll get to later in the year, and we'll then tie it back into this stuff, because these are not just randomly selected things. They do have to do with swapping your rows to swap our rows, and then the positives and negatives. But there is a lot of trigonometry built into where these come from, so we will discuss that later on in the year when we get into our trigonometry unit. So that's it for geometric transformations with matrices, and I will see you in class tomorrow, guys.